Hi, my name is Ryan Thompson, and this is my submission for question final exam for CPSC 5210. Evaluate the knapsack problem. In the original problem, this is the original problem. This is the matrix that you're given, but to observe the fact that a charger must go with their respective device. So to make the logic criteria easier in the code, I made a simplifying assumption to transform any two items that go together will be represented as one item with the summated value and the summated weight. So here, cell phone and cell phone charger get added to represent a weight of 130 or a value of 130 and a weight of 2. And laptop plus laptop charger get summed to $370 and 4 pounds. So this is just a simplifying assumption. It's not going to change the final answer, because if you chose one, you would have had to choose the other. You couldn't have chosen a partial of the two. So to illustrate this problem, here is the result matrix and how the score progresses over time, or not over time, but as you evaluate the different options for the items in this above matrix. The maximum value that you arrive at is $700 for the knapsack. And the items that you pick are all the cell phone items, which are the cell phone and the charger, the laptop items, which are the laptop and the charger for the laptop, and the medicine. So that's a maximum dollar value, and that's the items that are in the bag as well. So as you go through this, you have to first start to say, is the weight index above? If it's not, because you're going from 0 to 1, so you're always looping over W, the weights, and asking, is in or W sub n, so the weight item in, less than or equal to whatever the W has indexed over. And so the first one is 130 all the way throughout, because across the table, looking across the table, it starts off as 0 in the upper row, so there's no other information to add to it because the upper row starts as 0. So in the second problem, in the second item, its weight is 4 with the value of 370. So you have to wait until you get to greater than or equal to its current weight, and then ask, is the new weight plus the old weight greater than the current weight? Or is the value to the left here plus the new weight here greater than here? And after the iteration, that's when you add it. So you put the value in at 370 because it's greater, and then you say, is 370 plus 130 greater than 130? It is, and that value is 500. So 130 plus 370 equal 500. And you do the same thing again. You'll say, is 500 greater, or it's 370 plus 130 greater? It is. So you go through. And you're going to continue to do this. So we'll go down to an example here where you add the medicine. Now the medicine's the first of weight 1, but it's also the highest dollar per value, or dollar per poundage. So that's an interesting point. Here, we're at item 4, which is the medicine. Find the first value it's greater than or equal to, which is 1. course, 200 is greater than 0, so you put 200 in there. Then you go to the next stage. 0 plus 200 greater than 130? It is, so take the sum of these two. Now, is 200 plus 130 greater than here? It is. This is the value you get. And so you can see that same evaluation criteria is, if I add this value to a previously known iteration, can I get a new value? And so that's, again, the aspect of dynamic programming, is by using a matrix that stores the sub-results, you're able to call on those sub-results without having to completely redo all the logic and evaluation criteria. And so here's the algorithm for the knapsack problem. N represents the number of, or W here is the 0 to maximum weight, which is 7. And B represents the dollar value, which is actually what we're trying to maximize. That's our objective function, if you will, what we're maximizing over. So now we're going to look at each item, and we'll look at each incremental part of the total weight. So if the current weight is greater than or equal to K, if the current item's weight is greater than or equal to K, then you just bring the value, the previous value, down. You bring the previous value for that weight down. Else, evaluate, is the previous values at the current weight greater than the previous value plus the previous value at the previous weight? If it is, find the maximum of these two. So if the last iteration gave you a higher dollar value at weight 5, at pound 5, then adding, so if the incremental benefit of adding this item to create the 5-pound mark does not maximize dollars, don't do it. Take the previous value. So you're evaluating the maximum of this. So that's pretty much what you're doing here, is at every new item, you're looking at the marginal benefit of adding that at the current weight. So if you have 2 pounds, you have a dollar value. And now the next pound may be, the next item is 4 pounds. So you're saying, if I add this and go to 6, is there another marginal value than the previous 6-pound value I have? So you're evaluating to get to 6 pounds based on what I've solved so far. Is that the maximum dollar value? So this is good, but all it gives you is the dollar value. So if you want to know actually what items made it in there, we're going to do along the same lines, is that we're going to iterate over it, but you can't really integrate it into the previous problem, because you're still creating this matrix, so you have to do it afterwards. So what you'll do here is, as you go from item and weight, so as you go from across every row down, left to right, top to bottom, you'll be evaluating if the current value of the previous weight changed and the end value is greater than it made it in. So we go through here, it's all 0, so nothing got put in. Here we have our first change. 130 changed from 0, and its end value is greater than the previous end value. It made it in there. And again, we're not having to resolve all of this logic. What we're able to do is reference this matrix again. So Subproblem is the full problem represented, so this matrix represents all the solved problems. We can see here that the medicine made it in because its first change from a previous weight is at #1, and its end value is greater than this previous end value, so that means it made it all the way through and at one point wasn't stopped. Unlike here, where you can see adding the 10-pound weight gave a higher solution than the previous iteration at #2, but it didn't make it in there for the overall total weight. By the time you got to 7 and the total weight at #7 and evaluated all the marginal benefits, so it did not make it in there. And so we'll print the name if it makes it in there. And that's how you can come up with cell phone, laptop plus medicine to create the highest dollar value of 700 at 7-pound maximum weight.